yearn to know deep reality, so I start with what I know for sure, the deep structure of our universe. I say our universe, not the universe, because our universe is special in at least one way. We are in it. Is this trivial, patently obvious, of no value? This leads to the so-called fine-tuning of our universe. Here's the claim. Conditions that allow for complex structures, galaxies, stars, planets, life, brains, human beings, depend on a few fundamental constants of nature lying within tight ranges of values. And if these fundamental constants were to differ only slightly, those complex structures wouldn't exist. We wouldn't exist. That's the claim. But is fine-tuning valid? What's fine-tuning in cosmology? I'm Robert Lawrence Kuhn, and Closer to Truth is my journey to find out. The claimed fine-tuning of our universe presents a puzzle. Why does fine-tuning seem meaningful to some, irrelevant to others? To me, it's maddening. Is fine-tuning a real phenomenon? If so, it cries out for explanation. Discoveries in physics and cosmology convinced many scientists that, yes, fine-tuning is a real phenomenon. But recently, there has been pushback. Is there less fine-tuning here than meets the eye? When I hear of an international conference on the physics of fine-tuning, I decide to attend. This is no celebration of fine-tuning. The conference is held on the idyllic island of Crete in Greece, whose coastal splendor itself can seem fine-tuned. To pose the problem precisely, I begin with the co-author of a book on fine-tuning, A Fortunate Universe, Life in a Finely Tuned Cosmos, Welsh-Australian astrophysicist Geraint Lewis.
Geraint, you work in cosmology. What's the value of a fine-tuning perspective?
Well, the question really grows out of the research that's come out of the last couple of decades and this discovery that we have an accelerating expansion of the universe. We need some other energy density in the universe that gives us accelerated expansion. And we know that can't be matter, it can't be anything like normal materials.
Gravity, it's
Gravity
the
attracts. It attracts. So we need something to repel. So we find that we have this stuff in the universe, we really don't know what it is, so we give it a sexy name like dark energy. And when we look at the sort of energy density that we have in dark energy and compare it to our theoretical calculations, this is where there's this huge discrepancy. We have the observed values at 10 to the 120 times smaller than the theoretical expectations that we get.
Now, this is the so-called energy density of an absolute vacuum.
Yes.
So there's nothing in it. There's no molecules in it theoretically, no atoms, nothing.
That's right. So if you imagine you've got an empty box in the universe, when you add the quantum mechanical aspects, then you get particles popping in and out of existence, all this quantum vacuum stuff. And you can add up the energy density that's in an empty vacuum due to these quantum fluctuations. And that gives us this huge amount of energy per volume of space compared to what we observe. So the question is why does our universe have any of this stuff in it at all? In the past, matter dominated, and now it's thinned out, and now dark energy is taken over.
Because dark energy is the same in a given volume of space.
Yes.
Whereas as matter spreads out, the space grows, or the density of matter gets less, but the density of this energy doesn't get less.
That's right.
So it has a higher percentage of the total. Is that right?
Absolutely, absolutely. So we're now in an epoch where this stuff dominates, and it will now always dominate. So the question is then why do we have 10 to the minus 120th the amount of dark energy that theory tells us we should? And this goes back to this notion of the multiverse, whereby we have this inflationary epoch, we've formed all these little bubbly universes, and they've all got their own little laws of physics, and ours was born with this just sliver of dark energy left in there. So the question that we wanted to tackle is, well, what if our universe had been born with slightly different dark energy properties? So we can do this, right? We simulate chunks of the universe on a computer. We can put in the matter density soon after the Big Bang. The formation of stuff in the universe is a battle essentially between cosmic expansion and gravity pulling things together. So we have the mathematical framework. We can just put in the amount of dark energy. And again, at the start, it's always dormant because matter was such high density, but it means that if you make dark energy more concentrated at the start, then it comes to take over earlier and earlier in the history of the universe. And that's bad for the formation of things like galaxies. So we've got matter pooling together in the early universe. That crashes down, mainly dark matter, crashes down, taking gas with it. That gas pools to the center, forms a galaxy which is made of stars. In those stars, you create the elements that form you and I. If dark energy kicks in earlier, it can shut off that initial formation. And you don't have to increase dark energy by much, a factor of 10, possibly we could get away with it. We could still have enough time to form some galaxies. But you push high up to a factor of 100 times, etc., then you shut off galaxy formation. You shut off the formation of stars.
You say 100 times, that means from the discrepancy from 10 to the 120th, that would be to 118.
Correct. So we're still talking about a sliver of dark energy compared to the natural value. So again, we might have this sea of universes out there in the multiverse, and others have gotten crazy amounts of dark energy. Like if you've got the full amount of the theoretical expected, and boom, then there's a universe between every hydrogen atom, and that's it. No structure formation.
And if it went the other direction, if it got smaller and smaller or went negative, that would just cause an immediate attraction. So you'd have a sudden universe of black holes or something.
Absolutely. Zero would have been the best value. I said if it had come out to be none at all, everyone would have been happy.
Right, but then when you see something with 120 decimal places of zeros and then a 1,
yes,
you think you made a mistake and it really is 0.
That's right.
But that's not the case.
That's not the case. So you would hope that whatever the mechanism does, it would be natural to multiply by 0 so there's none left. But multiply by a factor to leave you this sliver, that's really worrisome.
Worrisome to me is a happy word. It means something is amiss. Are there things we do not understand? Are there deeper realities we have yet to discover? The cosmological constant, the so-called dark energy of the universe, seems incredibly fine-tuned. But is this really so? How to explore it further? What about other examples of fine-tuning in cosmology? I hear the co-author of A Fortunate Universe, Life in a Finely Tuned Cosmos, has a distinct perspective. Cosmologist Luke Barnes.
So the key standard model of cosmology we have has about 6 numbers in it that describe how the universe starts off and how it expands, the basics of how structure forms in the universe. The most famous one of these is known as the cosmological constant, but when we look at what would happen if it were different to what it is, you get disastrously rapid acceleration or deceleration. There's a small range that we're in where you can have structure form.
Okay, what are some others?
Well, one of the other important ones is the level of lumpiness in the early universe, this parameter called Q. It's when we look back to the cosmic microwave background, the lumps and bumps in that, this bit's more dense than that bit by 1 part in 100,000, so it's all very smooth. That sets the seeds for cosmic growth, for galaxies to form. But we can again play the game, what if that were different? If it were too small, you don't have the seeds there and the universe just stays smooth for most of its history and nothing forms. That's the end of that story. If it's too large, it seems like you might make galaxies that are a bit too dense. So you wouldn't have solar systems that sort of stay like ours is left alone for 4.5 billion years to make planets and all that things. Other stars would start wandering through, which is bad news for planets. If you make Q larger still, instead of making galaxies via this slow sort of clumping in process where you make stars and all that, you would instead make black holes.
What is Q?
It simply describes how large the variations are away from average density in the early universe.
Okay, so it's 2. What are a couple others?
Another one is how much dark matter and baryonic matter there is in the universe. And again, you have to sort of be in an interesting range there. Dark matter actually does help structure in our universe. Ordinary matter has pressure, so the pressure you see in a balloon. So as the gravity tries to make it collapse, it will fight back against gravity. But because dark matter doesn't have that, it can collapse earlier, so it helps structure in our universe.
Okay.
So if you had a purely baryonic universe, it seems like you wouldn't have as many galaxies, but a purely dark matter universe wouldn't make interesting structure because the dark matter doesn't seem to be able to do that. And so we're in a sort of interesting range there in the middle.
Any others of interest?
In the earlier stages of the universe, there's a relationship between the rate at which the universe expands and how dense it is. And so we're on this fine line that's called flatness. If that was slightly different, the universe would either recollapse too quickly under its own gravity, or it would expand so fast that no structure forms.
So basically what I hear is that there are a number of different characteristics that all lead to the same kind of fine-tuning result. So here's the question. Pick a constant. What does fine-tuning mean? What's relative? Maybe fine-tuning to you is not fine-tuning to me.
Yeah, so one of the things that you need to set up the problem is an understanding of what's the set of possibilities that this theory opens up. So the numbers in this theory are sort of part of that world that your theory creates. And so there's a set of possibilities that the theory determines. We have quite specific bounds on what that number could be within the theory itself. And so we can draw a line in the sand, here's where this number could be.
A Q, or the ratio of ordinary matter to dark matter is roughly what, 4/29 or 30 or something like that?
Yeah, something like that, yeah.
Yeah. So how tight is that ratio? Does that need to be? Is it, we're dealing with when it's 10% of that or 100?
Yeah. So the ratio of dark matter to baryonic matter actually seems, on the face of it, fairly wide. As long as they're kind of close to each other, we'd probably be all right. The problem is we don't know what sets those two numbers. The physics of dark matter and the physics of baryonic matter are totally independent. The fact that they would hit about the same number seems to be rather odd.
When you say about the same number, you mean the same order of magnitude?
Order of magnitude. Yeah. If you think of it as a ratio, it looks like in an order of magnitude either way, it will be all right for life, as long as you've got some dark matter to help you create structure, and you've still got ordinary matter to fall in and make galaxies.
And that's still fine-tuned, because in physics you can have orders of magnitude of not just one order of magnitude, but 40 or something.
Yeah, and especially if the physics that sets these numbers is totally different. If I say pick a number between 1 and a trillion and pick another number between 1 and a trillion, if you end up with numbers of the same order of magnitude, that's kind of interesting. It's not a totally clear-cut case, but there's still an interesting thing perhaps there to be explained. Why are these numbers close to each other?
Are all astrophysicists entranced by the apparent fine-tuning of the universe? The key question is the tolerance ranges of fundamental constants. Like blood tests that show in or out of range, can structure in life show which values work and which do not? If so, rather than asking whether our universe is fine-tuned, can I ask the question in reverse? How much fine-tuning would it take to make other kinds of universes friendly to life? I speak with an astrophysicist who's something of a fine-tuning skeptic, working on star formation and cosmology, planetary habitability, and the long-term future of the universe, Fred Adams.
Fred, fine-tuning is to me a probe of what the universe is and potentially what it's all about. One test of fine-tuning is making alternatives. What would it take to make other kinds of universes habitable?
Yeah, we can talk about some of the basic parameters. The universe contains matter and a weird kind of energy called dark energy. And the matter consists of regular matter, the baryons, the protons and neutrons that make up you and me, as well as dark matter, which we're still trying to figure out.
Right.
So you can imagine other universes with different mixes of those ingredients. And the key question in fine-tuning is what range of ingredients will allow for a habitable universe? And if our universe is fine-tuned, the answer would be you can't go very far from the particular set of ingredients we have. One of the structures that you're talking about is that somehow in the early universe, the universe makes fluctuations in the matter fields, which means there's little bits that are denser and little bits that are less dense. The amplitude of those fluctuations is a key cosmological parameter.
Right.
And another key cosmological parameter is the amount of baryonic matter, or protons and neutrons, relative to the number of photons.
Okay.
The question is, how low does it have to be before it fails, and how big does it have to be before it fails?
And failing means that you don't have a habitable universe because you don't have the right structures.
Yeah.
The ratio between protons and photons.
Yes.
Why is that critical?
In the early universe, our universe processes about 25% of the protons into helium during the first 3 minutes of our history. If you process all of the protons into helium, thereby leaving no protons left, you need protons for the H in H2O, also known as water.
Right.
And without water, we're not the same.
Right.
So you can kill the universe if you're able to make all of the protons synthesize into helium in the first 3 minutes.
So that would be if there's too many protons relative to photons.
Yeah, so if the universe has a higher ratio of protons to photons, then matter domination starts earlier, which means structures can form earlier. And that can give the universe more leeway in forming its structures. You can get away with a lower amplitude.
So what the claim is that our universe is not necessarily the best fine-tuned universe for the creation of complexity and structure.
That is true. In fact, I would argue that if you and I were to sit down at the blackboard, it might take us many years, we could design a better universe. And I've been trying to do that, right?
Nobody ever accused you of modesty.
No one's ever accused me of that. So a better universe would have larger fluctuations. And the reason is that would make structure formation easier, more robust, and the theories that we have, which are premature, are easier to understand if that fluctuation level is larger, not smaller. So if the amplitude is larger than in our universe, it's easier for an inflationary theory to work. It's then easier for the universe to make galaxies and then stars and planets and people.
And it happens more quickly.
Yeah, it happens more quickly, it happens more robustly.
Right.
Now, there is a danger of going too far,
Obviously.
in which case you get the galaxies to be too dense.
Right.
Too many things in the middle will collapse to the black holes that form in the middle of the galaxies.
Right.
And if the stellar environment is too dense, you can kill the universe in two ways. You can have the stellar flybys so frequent that you'll strip planets off stars. And you will also have the background radiation field so intense that it's too hot. However, there's sort of a sweet spot. If you make the galaxy the right density, then you can make the background night sky the same brightness as our day sky. Then every planet is habitable. And that's actually a better universe than ours, because then all of the planets in that sweet spot will be habitable, at least they'll have the right temperature. And that's not as constrained as our universe.
Is there a possible danger that in your constructing a universe that would be better than ours, you're actually leaving out some things that you don't know? I mean, that seems like...
Oh, that's a very valid critique. And in spite of my seeming arrogance, we are well aware that we actually do not understand all the things that we need to for life.
If Fred is right, other kinds of universes could be more efficient in producing life-bearing structures like planets, which would seem to suggest that fine-tuning in our universe is not as fine as advertised. Again, the importance of fine-tuning turns on how narrow or how broad the tolerances around fundamental constants, while still being consistent with the formation of stars and planets, and with sufficient time for the generation and evolution of life. But is there a still deeper critique of fine-tuning? I meet a pioneer in transforming cosmology into a precision science, one of the organizers of the Physics of Fine-Tuning Conference, Joseph Silk.
Joe, to see the application of fine-tuning in cosmology, are there other areas of cosmology that lend itself to a fine-tuning kind of analysis?
Okay, so here's maybe the most basic example of all, the sun, okay? So why is the sun the mass that it is, and why are all the stars in the universe the mass of the sun within a factor of 10 or 20, okay, or 30, whatever? You know, they could be much more massive, they could be rocks, they could be moons, they could be almost anything. So one of the early realizations in fine-tuning studies was to say, well, the sun is a competition between the force of gravity and the outward pressure of the radiation. And there's a natural balance between those two, which you can express in terms of two fundamental constants of nature. So one is the fine structure constant, which controls all of chemistry basically, and the other one is the gravitational analog of that, which is the ratio of gravity to electromagnetic force between a pair of electrons or protons. Okay, so you take a gas cloud, let's say, and you ask the question, let's imagine it gets colder, it breaks up into smaller bits. The smallest bit might eventually form a star. And what you find when you do this fragmentation calculation to try to form a star is that you can express the minimum size of a fragment in terms of fundamental constants, but you get the wrong number. You don't get the mass of a sun, you get the mass of a planet. Oh. And it can't be a planet because at the beginning you didn't have the silicates and the iron that the planets are made of. So the calculus is simply wrong. And so you learn, when you look at this more carefully, with more physics and more understanding, that in fact you make these minimal size lumps, dense clumps of gas, but then stuff accretes onto them, okay? It's different physics. It's not just physics of fragmentation, it's physics of growth. And it doesn't stop there either, because then you suddenly realize, well, if growth then determines the final size of my gas clump, why does it stop at the mass of the sun? It goes into hundreds of thousands, it could become a black hole. And then you realize that no, what happens next is that as this clump gets roughly the mass of the sun, it starts producing what we call feedback. It gets hot enough, and any magnetic lines of force therein get tangled enough to give you forces that stop the gas accreting. So it's a combination of, first of all, the fundamental fine-tuning, which gives you the basic scale, plus complex physics, in this case accretion and feedback. And so that means what we once thought was fine-tuning is really nothing other than complexity, basically. We're here by self-regulation, you know.
And that self-regulation, though, is that kind of a fine-tuning itself?
Well, you know, in some other universe where these constants might be very different, you'd end up with different mass stars. But what we see around us is the result much more of complexity and self-regulation than any initial choice of the fundamental constants. That's what one has to realize.
And obviously you have to have enough pressure and temperature to cause fusion.
Yeah. It's all force balance, but coupled with highly nonlinear physics. That means you don't even recognize what went into it at the beginning. And it all comes from self-regulation. And I think the same is true in biology or consciousness. If you want ever to explain those, you'll find yourself tackling with similar arguments that are very, very different from fine-tuning.
Interesting. Are there other examples in cosmology?
Well, there, for example, is the mass of a galaxy. Why is the mass of a galaxy the way it is? And again, it turns out that you can calculate, you know, the mass of a big gas cloud, and it turns out it's a balance again between gravity, causing it to collapse, and the rate at which it can lose energy by atomic cooling, atoms bouncing into ions and electrons and things, exciting them and then radiating. And that gives you a natural scale. Clouds too big cannot lose energy, therefore they stay hot, therefore they cannot ever make stars. I can calculate the average mass of a galaxy. We can learn why the Milky Way is the mass it is. But when you go to the surveys of galaxies, you find that most galaxies are very small, and there aren't that very many very big ones. And if you go to a theory of structure with only dark matter in, then it predicts too many small galaxies and too many big galaxies compared to what we see by enormous numbers. So again, something else is needed. And so this again is complexity and self-regulations.
Can fine-tuning probe the nature of the cosmos, offer clues to the mystery of existence? Fine-tuning is often deemed a fact and used to reach grandiose metaphysical conclusions by philosophers, theologians, and even physicists. But does fine-tuning truly cry out for explanation? Not if other universes could be tuned better. Not if fine-tuning reflects deeper mechanisms. Is there sufficient evidence to take fine-tuning seriously? If so, which I believe, then ask, how might fine-tuning come about? There seem only three kinds of answers. Two are natural, one is not. One, a new deep physics yet to be discovered, which would constrain the fundamental constants to be only that which they are and nothing else. This looks less likely. Two, A multiplicity of universes, a multiverse, each with its own set of laws, and only in those rare cases where structure in life is possible can sentient beings arise and marvel about fine-tuning. 3. A causative mechanism beyond naturalism. Though to some this would be God or something like God, there are other candidates, however bizarre, such as alien simulations and quantum theories of retrocausation. Fine-tuning, I bet, helps us get closer to truth.
For complete interviews and for further information, please visit closertotruth.com.